Okay, so welcome back to another video of computational methods, where in this video we're going to explore the case of a power generation turbine. The question at hand is, what is the maximum power generation? And this will occur when the gearing is at a gearing of 1 to 3, and we're going to find the why and the how of that as well. The mechanisms by which we're going to achieve this is a momentum balance and a kinetic energy balance. So let's go off with that explained. Let's go off and take a look at our situation. Let's say we have a power generation turbine. It may be a windmill, it may be water, it could be from steam generation from a natural gas power plant, any sort. Okay, and this turbine, we don't necessarily care what the design is, how many blades or the shape of the blades. What we do care about is this cross-sectional area. We'll call it S, in which the air is influencing the turbines and causing it to turn, therefore generating electric power. So we also have to designate some control volumes, and it's that, well, we have air of some velocity. I am saying air, maybe that's just by habit. We'll go with air for this case. We have air of some velocity going in, and obviously the velocity going out will have to be less than that, because we're taking away energy, we're turning that energy into useful work. One more thing is we are assuming maximum efficiency, meaning all of that energy conversion is entirely turned into work. None of it is lost to heat. And it's interesting to see that despite the fact that we have maximum efficiency, there's only so much power we can extract from this. And that's because, well, if we extract all the velocity away, then we'll have just this barrier of immobile fluid that will prevent any more movement. So it would make sense that we cannot take all of that velocity to useful work. Okay, so with that ramble out of the way, we know that the velocity going out is less than that, and in order to compensate for that, the cross-sectional area of the fluid associated at position 2 has to be greater than 1. Okay, so let's go off and define our momentum balance. And the momentum balance is that, well, we have dmv momentum of the system. Okay, reminder here, we were going to define the system at the very beginning as the fluid at the position in which the fluid can influence the turbine. So the system is not the turbine, but the system rather is the fluid. Okay, so the change in momentum with respect to time is equal to the velocity at position 1. Let's do position, yeah, we'll do position 1. Position 1, and the mass flow rate at position 1. Notice how I'm not calling it in and out, because that kind of pigeonholes us into a definition of in or out. That with different designs, there may not necessarily be an inlet and an outlet of a particular power generation turbine. So we'll call this position 1 and 2. Okay. Plus the velocity at position 2 multiplied by the mass flow rate at position 2 plus any associated forces. And this is what we're after, the associated forces. One thing that we are assuming is that we are at steady state. Okay? In steady state, as we've always done this semester, is that when all derivatives with respect to time go to 0. Okay? So that goes to 0. Another thing about steady state is that, well, steady state would imply that we should not have any mass accumulation or consumption. In other words, the mass flow rate of 1 has to equal the mass flow rate of 2, which we can just call the mass flow rate in general. This mass flow rate can be defined by rho multiplied by the velocity at the position in which the turbines are being influenced, multiplied by the cross-sectional area of our control volume that we have defined, rho vs. Okay, so what will this look like? This will then look like 0 equals v1 plus v2 multiplied by rho vs plus the associated forces. We can bring the associated forces to the other side. Negative F equals v1 plus v2. So we are talking about power generation. So what does that necessarily mean? Recall that power generation, power is defined as the force multiplied by velocity. Okay, so what is that? Newton times meters per second. In other words, joules per second, or watts. Okay, so that's the definition of power. So we can. Oh, I forgot the rho vs. We can use this expression to substitute for our expression of associated forces, such that the power can be defined by negative v1 plus v2 multiplied by rho v squared s. Okay, and we have this expression here, and at this point we'll have to go and bring in the idea of a kinetic energy balance. But take a note here, just so we don't get lost. V1 is the velocity at position 1, the velocity of the fluid. V2 is the velocity of the fluid at position 2, and V, normal V, is the velocity of the fluid at our specified control volume. Rho being the density of the fluid, and S being the cross-sectional area in which the fluid is influencing the turbine blades. Okay, so we have some unknown values, and we're going to remedy that by bringing in an idea of a kinetic energy balance. Okay, so now what we have an expression. By the way, I did make a mistake in the previous segment in which I had incorrectly defined the momentum balance as a matter of addition. In reality, it should be subtraction, in minus out, and this carries all the way down to here. Okay, v1 minus v2. So how do we deal with this? Well, we have this expression v, v being the velocity of the fluid at the contact at the turbine. So that's something that's rather difficult to measure. We can easily measure the velocity of the fluid before and after the turbine, but not quite exactly at the turbine. So ideally, we'd like to get rid of this somehow, and this will come in the form of doing a kinetic energy balance alongside our momentum balance, and it'll look something like this. Power can also be defined as the change in kinetic energy per unit mass multiplied by the mass flow rate. Okay, and we've seen this particular expression before, kinetic energy per unit mass, in the Bernoulli's equation, particularly in the velocity term. So v1 squared minus v2 squared over 2. Okay, multiplied by mass flow rate, which we've defined earlier in this video as rho vs. Okay, so how is this kinetic energy per unit mass? Well, if you recall from your basic physics class, you know that kinetic energy is 1/2 mv squared, the units of which are kilograms multiplied by meters squared over seconds squared. Okay, so what is this? This is a change, right? It's a difference in two positions, and the velocity is meters squared over seconds squared, but without the mass. Okay, in other words, we're dividing it by mass. So this is kinetic energy per unit mass. Okay, so there's the explanation behind that. Now, what do we have? We have two different expressions for power which describe the same thing. So next step is obvious. We should equate them. So v1 minus v2 rho v squared s equals v1 squared minus v2 squared over 2 multiplied by rho vs. Some obvious cancellations, which are rather nice. Get rid of that cross-sectional area and fluid density, and we don't have to worry about any of that. So now comes the question of, what do we solve for? Again, we are solving for that velocity v, which is rather difficult to measure experimentally. So v equals, I'm going to expand this difference of squares out, so v1 plus v2 v1 minus v2 over 2 multiplied by the reciprocal. I'm bringing this expression over, right, over to the other side, so divide by v1 minus v2 all everything else cancels out, so I'm all good. So another convenient cancellation. So what do we have? We have the velocity. The velocity is equal to v1 plus v2 over 2. Hey, that looks familiar. Looks like an average of the velocity before and after the turbine, right? So logically, that makes a lot of sense, and it also makes a lot of sense mathematically. So let's go ahead and plug this back into either expression for power, doesn't matter. I'm going to choose this because it makes my algebra life a little easier. So let's bring that to the next page. Okay. So, what do we have now? We have expression of power, and we can replace that pesky velocity term. The velocity, not 1, not 2, just normal velocity at the turbine. So, power is equal to what? Let's do this in red. Power is equal to v1 squared minus v2 squared over, let's multiply this. 2 times 2 is 4. This quantity multiplied by the quantity v1 plus v2, okay, multiplied by rho s. So I'm going to keep all my constants out front. I have power is equal to rho s over 4, multiplied by, and I'm going to multiply all of this velocity out. We have v1 cubed minus, or rather, v1 cubed plus v1 squared v2 minus v2 squared, or let's keep this in the same order, v1 v2 squared minus v2 cubed. So now what? Well, as it turns out, for the purposes of energy generation, for those in the field of energy generation, it's rather convenient to describe things in terms of gearing. In other words, the ratio of my velocity after and before my turbine. Okay, so that's the idea of gearing. So how do we get that? Let's go ahead and let's factor out a v1 cubed. Okay, so power is equal to rho s v1 cubed over 4 multiplied by what? Multiplied by v1 cubed over v1 cubed is 1 plus v2 over v1 minus v2 squared over v1 squared minus v2 cubed over v2 cubed. Hey, we have a bunch of expressions which are the same. And what have we always done? Call it something else, right? So we call it r arbitrarily. R is going to be my gearing, the ratio of the velocity after and before my turbine. Okay, so now what? We have power is equal to rho s v1 cubed over 4 multiplied by 1 plus r minus r squared minus r cubed. So let's remind ourselves, what's the whole point of this? We're trying to look for a maximum energy generation. So maximum, minima, what does that sound like? Calculus 1, right? I realized that this should be a S. Calculus 1, right? Remember from calculus 1, the first derivative, the roots of the first derivative will describe the minima and maxima of my original function. So dp dr is equal to rho s v1 cubed over 4. That's all constants in this context, so I don't need to worry about it. And this is equal to 1 minus 2r minus 3r squared. Factor that, solve for the roots. I have 1 minus 3r. 1 plus r? Double check. Yep. Minus 2r plus 1. Okay, good. Factoring out works out. So a negative root doesn't make any sense in the real world context. So this r equals negative 1 is useless. But how about this? R equals 1/3. Hey, that's in our problem statement. As it turns out, in order to get the most efficient power generation, the gearing of my turbine has to be 1/3. Okay, so over here, what's that? Occurs when the ratio of the outlet to inlet velocity is 1/3. Betz's law. Okay, so that's where that comes from. So a rather easy proof. If I can get back to my notebook, there we go. So what's next? Hey, let's plug this back into my expression for power to find out what my maximum power is, right? We solve for the root of a derivative. We're told that this maximum power generation occurs at a gearing of 1/3. What exactly is that maximum power? So let's do that. Power is equal to rho SV1 cubed over 4. So this is really testing my powers of algebra here. 1 plus 1/3 minus 1 over 9, okay, minus 1 over 27. So fraction jazz going on. The common denominator is 27. So what do we have? We have 27 plus 9 minus 3 minus 1. I think I believe I did that correctly. So this becomes what? 4, 5, 27 plus 5. We have 27 plus 5 is 32 over 27. So power is equal to rho SV1 cubed over 32 divided by 4. We still have that 4 out there. Is that's not that is not. Oh, that is divisible. That is 8. 32 divided by 4 is 8. So we have 8 over, this is seriously testing my mental math skills, 8 over 27. Okay, so there we have it. This is the final expression for the maximum power generation when the gearing is 1, 2, 3, according to Betz's law. And we, along the way, went ahead and proved Betz's law as well. So with this final expression, this will conclude this video, and I will catch you in the next one.